Hi, in this video we'll examine whether an impossible trampoline can defy the real-life application of the conservation of energy principle. We'll first start with what an impossible trampoline is. As anyone who's used a trampoline will tell you, without applying additional work in the form of pushing against the surface of the trampoline, you won't rise as high as you originally were, and will gradually rise lower and lower with each bounce. An impossible trampoline conserves energy so well that you can reach your original height without extra effort. Here's some examples of impossible trampolines. To evaluate whether these trampolines truly conserve energy absolutely perfectly, we can first start with the energy principle, recognizing that if energy is conserved and made up of both kinetic and potential components, then as one form of energy increases, the other will decrease, and vice versa. We know that our potential energy will be comprised of both gravitational and spring or elastic components, with formulas shown here. Prior to jumping, there is no kinetic energy as the person is at rest, and there is no spring potential energy, given that there has not been any interaction yet with the trampoline. So all energy is gravitational potential energy. After the person jumps, there is motion, and as such, there is kinetic energy. And as the height between the person and the ground decreases, the gravitational potential energy decreases as well. Upon landing on the trampoline, the person is temporarily at rest, making the kinetic energy equal to 0, while the gravitational potential energy is at its lowest value. The bulk of our potential energy is converted into spring potential energy, brought about by the deformation or sinking of the trampoline when you land. As the person bounces back upwards, there is kinetic energy as well as spring potential energy converting back to gravitational potential energy as the distance from the ground increases. I analyzed one particular jump made on a seemingly impossible trampoline in tracker software to evaluate its energy conservation. As you can see from the Y position versus time graph on the right-hand side of the screen, the trampolinist does not quite reach his original height, giving an indication that there is some energy lost, given that he does not appear to push off from the trampoline upon landing. We can use the information gathered from Tracker to solve for the spring constant needed to solve for our spring potential energy. Using the guess that our jumper weighs about 165 pounds and that our period of oscillation is 2.1 seconds, we get that our spring constant is 669.61 newtons per meter. We can then use the energies present at the moment our jumper lands on the trampoline to isolate and solve for our trampoline deformation, assuming that the height between the ledge and the trampoline is about 1 story high. Using that, we get that our deformation is 2.69 meters, which seems really big, making me believe that the height was not quite 1 story. Using my assumptions, which are not seeming right, I plugged in our energy components as well as the tracker software into the Python to graph our change in energy, and my code refused to work, which is unfortunate. However, I can surmise what my energy graph would look like based upon knowing how the kinetic energy fluctuated during the jump, and how our potential energy changed from gravitational to spring and back to gravitational potential energy, which we can see here. In conclusion, even without the Python, we can answer our original question that the trampoline evaluated does not defy the real-life application of energy conservation, and that there is energy lost, given the lost jump height and the lack of push-off from the trampoline surface. Thanks for watching!